Hello, and welcome to what is already the 7th episode of this Bits of Q series on template metaprogramming in C++. And after all these episodes, it is time for us to face the facts. Almost all real-world projects use runtime data. As such, in this episode, we will start looking at how we can use our metaprogramming techniques to, at compile time, figure out how to manipulate data that exists at runtime. To do this, we'll be using the classic example of the standard tuple. The tuple is quite an interesting class. It allows you to store an arbitrary set of elements regardless of their types. To do this, the tuple is implemented as a variadic template, where each of the template arguments are used to represent the types of the corresponding elements. As such, when creating a tuple, as well as when manipulating your tuples, a decent amount of metaprogramming is involved. For example, say I have this tuple t1 containing an integer and a boolean, and this tuple t2 containing a float and a char. I can use the standard library operation tuplecat to concatenate these two tuples. There are basically two things that need to happen to make such a tuplecat operation work. First, at compile time, you need to figure out what the type of the output tuple should be. This is a classic metaprogramming problem, similar to the ones we've discussed in previous episodes. But this time, once we know our output type, we are not done yet. We also need to figure out how to map the data from the input tuples to the elements of the new concatenated output tuple. Depending on the internal representation of the tuple data, this may also need a decent amount of metaprogramming. And of course, when such an operation is executed at runtime, you want to make sure that it is efficient. This mainly involves ensuring that no data is copied or moved more often than is needed, as you go through the often recursive process of building up your output tuple. As such, this episode is going to combine both elements of metaprogramming as well as techniques for optimally handling your runtime data. We will be talking about L values and R values, and we will apply perfect forwarding. If you're not that familiar with these topics, I recommend you check out my tutorial on perfect forwarding and perhaps move semantics before continuing. You can find the links in the description. This brings us to the question of what is a tuple? And I don't mean in the philosophical sense, but rather what does the tuple data type look like and how does it represent its data? And there are basically two approaches to creating a tuple class. You can use recursive inheritance, or you can rely on multiple inheritance. I'll briefly explain both, starting with recursive inheritance. In this approach, a tuple is only responsible for its first element. The rest of the elements are handled by the recursive base classes. In this example, where we have a tuple of int bool char, this class would have a data member to store the int element. To also store the other elements, it will inherit from a tuple of bool char. This tuple, in turn, will have a data element for the bool, and it itself will inherit from a tuple of char to store the last element. Because all member variables have the same name, data, we can't easily access different elements from the main tuple class. To access a certain element, you need to cast to the base class that has that element as its first template argument. This is exactly what the standard get function does for you. The second approach uses multiple inheritance. Ideally, if you have a tuple of int bool float, you just inherit from those three types, which makes accessing them a matter of casting your tuple to the correct type. Of course, this approach has a big problem. If two of our elements have the same type, we'd be trying to inherit from that type twice, which isn't allowed. To work around this limitation, you can use a unique wrapper class for each of the elements. A common approach is to create something like this. This tuple data class represents a single element of type t. By using the index of the element as one of the template arguments, we can guarantee that this type is always unique among the base classes of a single tuple. If we now go back to our tuple of int bool bool, it would have the base classes tuple data 0 int, 1 bool, and 2 bool. At this point, we can access the second element by again casting to the correct base class. In this case, tuple data 1, bool. So, Should we go for the recursive or for the multiple inheritance strategy when implementing our tuple? Both methods are good candidates, and each have their own pros and cons. For this metaprogramming series, however, there are two main aspects that are important: simplicity and performance. In general, recursive tuple implementations are a bit simpler, as are the algorithms that manipulate them. For example, as I said before, implementing a get function boils down to finding the correct base class and casting to it. With the extensive metaprogramming library that we have built up in the previous episodes, we can easily do the type manipulation needed to find this base class, given an index and a tuple. Therefore, we will go for the recursive approach in this episode. However, the multiple inheritance approach gives us more options for optimizing the compile time of algorithms that manipulate these tuples. As such, we will revisit the tuple algorithms we develop now later in this series, when we discuss high-performance metaprogramming techniques. At that point, we will also implement the multiple inheritance version of the tuple class. Okay, I think I've made you wait long enough at this point. So let's start writing some code. In contrast to the previous episodes, we will not be using Compiler Explorer today. As we are developing more and more code, it has become time to split everything up into separate files and move to using a fully fledged IDE for our development. The metaprogramming library, which we have developed in the previous episodes, has been moved to this metaprogramming.h header. Aside from some include cards and the addition of a license statement at the top, it is exactly the same as before. I also already created a tuple.h header in which we will implement our tuple this episode. You will of course still be able to find all code related to this series online. I have set up a GitHub repository just for this purpose. There's a link in the description. I also set up CMake, which allows you to easily compile the code on different platforms. Currently the code has been verified to work with GCC and Clang on Linux, as well as with MSVC on Windows. Okay, let's get started with our tuple. A tuple is a variadic template with its elements as template parameters. This main template definition will be the fallback for our tuples without any element, and we will define a separate specialization for those with at least one element. As such, we can already add a default constructor here, which will make const export to allow our tuple to be used in a const export context, just like the tuple from the standard library. Now, let's create a partial specialization for the tuples that contain at least one element. As we will use the recursive approach to defining our tuple, we can simply define a data member that is of type lm0, and make sure that our tuple inherits from itself, but now with the remaining template parameters as its parameters. As for the constructor, we make it const export again, and also mark it as explicit, as it is callable with only a single parameter, and we don't want any ambiguity with the implicitly generated copy constructor. Regarding the input for the constructor, we will first write a naive version, where we take our elements by value and set data accordingly. We will upgrade our implementation later to more optimally handle its data at runtime. The classic way of constructing a tuple is using the makeTuple function. So let's also add a makeTuple for our tuple type. The advantage of using makeTuple is that we can use template argument type deduction and don't have to explicitly define our template parameters when creating a tuple. We will use auto return type deduction as we want to return a new tuple by value. Again, we just take our inputs by value for now. We will do this in a smarter way later. Before we start to type out an implementation, let's have a quick look at how the makeTuple function from the standard library is defined. I opened up CPP reference here, and as you can see, it has this paragraph describing the relation between the types ti in types, the template arguments to our makeTuple, and the types vi in vtypes, which are the template arguments to the tuple that is returned by the function. It is not a trivial relation, so let's have a look at the possible implementation section to see if we can make it a bit more concrete. Here we see that they suggest some small meta functions to implement a unwrap revdk, which can be used to get the correct tuple element type given the corresponding makeTuple template argument. Luckily for us, this function is actually part of the standard library nowadays. So, back to our code. Thanks to 0+20, our make tuple becomes a simple one-liner. We will return a tuple of std unwrap revdkt of our elements. Note that we are expanding the parameter pack after the closing bracket. So this will expand into a comma-separated list of unwrap revdkt elements. For now, we just pass the input elements to the constructor directly. Now, let's check if this all still compiles. It does. Although, admittedly, that doesn't mean much, as we have not tried to instantiate any of these templates yet. So let's go back to our main and test our new tuple class. We'll create a tuple of int, bool and double. As you can see, I have a pretty rigorous set of warnings enabled in my IDE, as it already starts complaining that the tup variable is unused. I don't really care about this, so I'll just add a maybe unused attribute to suppress this warning for now. It looks like we have a working tuple class. As a quick sanity check, let's see if we can access its first element using the data member directly. Because of shadowing, this should refer to the data member of the most derived class, which is our complete tuple, and as such, it should refer to our integer. And indeed, we see that it returns the value 8. Before we continue to create a get function to allow access to our other tuple elements, let's add some more modern C++ features to allow template argument deduction when using the constructor of our tuple. If we now try to create a tuple without specifying its template parameters, we will get an error. No viable constructor or deduction guide for deduction of template arguments of tuple. And that makes sense. What is happening here is that the compiler doesn't know how to deduce the types for these template arguments based on the inputs of our constructor. This is because we are only using E1 directly and are simply passing on the parameter pack to our base class. So we need to tell it explicitly how to deduce these. And we can do this by creating a so-called deduction guide. Deduction guides are a C++ 17 feature and are defined outside of the class or struct for which they define the type deduction guide. For symmetry, I like to use the same configuration of template parameters, one type name and one variadict parameter. But the deduction guide does not have to correspond to any of the constructors of the class for which you are defining the guide. It is just saying that if we want to construct a tuple using some parameter E1 of type T and possibly more parameters of type T's, then the compiler should use as constructor tuple of unwrap revdkt of T followed by unwrap revdkt of our T's. This is all that's needed to define a deduction guide. It simply explains the relation between the arguments used for construction of a tuple and the actual constructor that needs to be called to do this construction. And if we compile now, we see that it all works. Just as a sanity check, we can again output the value of the data member, which is indeed 1, as it refers to our first element. Okay, now for accessing data other than our first element. And once we've done that, we'll look into making our code a bit more efficient, because, again, we are currently unnecessarily copying values left and right. In other words, let's create our own get function. We'll write the original C+11 version of get, which is a get by index. So this index will be our first template parameter, and we'll use the second one for our input tuple. Just like the real get from the standard library, our get will also be const expr, and we will use decal type auto here as a return type. Decal type auto return type deduction is different from auto return type deduction in that it can also deduce reference types, which is what we want for our get function. If you want to know all about the differences between auto and decal type auto return type deduction, check out my video on type deduction in C++. Link in the description. For now, we'll make our input a simple reference. And now we just want to return our element here. So how can we access the element in our tuple? Let's first delegate our get function call to a struct, allowing us to use partial specializations. We'll be creating a getImpulse struct in a detail namespace. Pass it our index I, and we'll pass it the std remove revt of our tuple. The reason we strip off the const and volatile qualifiers, as well as whether it's a reference or not, is because that allows us to more easily manipulate this tuple type, which is essentially a type list, with our metaprogramming library. Then, this getImpl struct will provide a get function where we pass the actual tuple instance. For the main template of our getImpl, we'll again accept an index I and our tuple. And now we'll start using our metaprogramming library. We'll say that getImpl inherits from getImpl I-1 of the pop from t of our tuple. So this is where the recursion happens. We'll repeatedly recurse on our tuple, but then without the first element, until we reach the point where our index is 0. At that stage, we know that the data member contains the first element of our now smaller tuple, and that this corresponds with the ith element of our original tuple. As I said, at some point our I will be 0, so we create a partial specialization for that case. And this is where we create our getMember function. We'll use a template parameter to represent our input tuple here. Because the tuple template argument of our getImpl struct has now been modified, and hence we cannot reuse it here. And furthermore, by using a template parameter here, we can deduce the exact type of our input tuple, and in particular whether it's const or not const. We'll make our get static so we can easily call it. Again, returning decal type auto, so references are preserved. And for now, we'll just accept our tuple as a normal L-value reference. Now this is where we need to do this casting, which we talked about at the beginning of this episode. The input of this function has the original complete tuple as type. And now we need to cast it to the reduced tuple type of our getImpl struct template argument, so we can access the correct data member. For now, we'll just assume that our input tuple is not const, just like our tuple template argument. So we can just do a normal static cast to a reference of tuple, and then we return the data member. And this gives us a very rudimentary version of a get function, which should work when passed a non-const L-value tuple. To test our get, we'll request the third element, index 2, of tup2, and we expect this to return 4. Bam, 4. It seems to work. But our get is still quite limited. If I make our tup2 a const tuple, we will get an error. Binding reference of tuple to a value of tuple drops const qualifiers. And if I quickly compile, I can easily navigate to the point in our code where this goes wrong. It is our static cast to a reference to tuple. For the template argument, we removed the const and volatile qualifiers. So we need to cast to a const version of this tuple type if and only if our input tuple t is also const. We'll add a const expr bool isConst, which we define as std isConst v of our t. We then say, if const expr is const, we again return the data of our casted tuple, but now we cast to a reference to const. Our get now works for both const and non-const inputs. Let me just clean up our test a bit and make sure that we have both the const and non-const tuple covered. So, it now works for L values, but what about R values? If I try to call get on a tuple that I create inline here, so the input is now a temporary, an R value in other words, indeed, we get an error. No matching function call to get. It continues to explain that the candidate, which we defined before, expects an L value for the first argument. So let's update our get so it can handle both L values and R values. In other words, let's apply perfect forwarding. Instead of expecting an L value reference here, we are going to accept tuple as a forwarding reference. And now that we're at it, let's just do all the forwarding needed to optimally pass our inputs through both get and getImpl. So we forward into getImpl, and then we arrive here. Again, we update our input to be a forwarding reference, so it can handle both L value and R value inputs. And now we should be careful. As a forwarding reference always deduces to a reference type, we need to strip off this reference before we can pass it to std isConst v, otherwise it won't work correctly. Now we need to add some more cases to deal with R value inputs. We'll first add a const expr bool isLvalue, for which we can use std isLvalue reference, because, again, a forwarding reference always deduces to a reference type. Our first case now only holds when a tuple is both an L value and its const. we update our second case to rvalue and non-const. Then we have the case where we are passed a const rvalue. This is kind of rare, as a const temporary doesn't make much sense in most cases, but for completeness, we'll support it anyways. And of course, we cast to an rvalue reference here to make sure we maintain our value category. Lastly, there are the normal non-const rvalue references. And now everything compiles again. We have just created a get function that can optimally accept all possible input cases. Although there's still one big problem with our get. Yes, we can accept L values and R values, but we can't assign to the elements that we retrieve yet. If I try to get the third element of our tup, you'd expect us to be able to assign to this integer, but instead we get this expression is not assignable error. And this is because the wrong return type is being deduced. Yes, we use decal type auto, which can indeed deduce a reference type, but we are not passing it a reference type. We are passing it those data members, which have a value type. So we need one last cast to fix this. To figure out what type we need to cast to, we will again invoke our metaprogramming library. We know that our data member has the type of front t of tuple. And then we just explicitly cast our data to the correct reference type for our 4 input categories. And now our assignment also works. Let me quickly demonstrate this. If I output element 3 after assigning to it, we indeed get 4.2 returned. Awesome. Our get works, our tuple works, we are done now, right? Not yet. Functionally, both our get and tuple work, but performance-wise, our tuple is still quite inefficient, as it is doing a lot of unnecessary copies. So, for the final section of this episode, I want to also apply forwarding to our tuple class. And we'll be using a little trick here to help us do this correctly. We will just use our compiler to count the number of copies that it moves for us. To do this, we'll use a small test utility, which I like to call copy counter. Let me just put it in a new test utilities header. And I don't want to spend too much time on this utility, so I'll just copy paste the class in directly. A copy counter is a very simple class. It has a static member variable of type copystats, in which it's going to keep track of the number of times it has been default constructed, copied, or moved. It can do this because we've declared overloads for the construct, and copy assignment, the move construct, as well as the move assignment operations. And in each of these overloads, we just increment the corresponding counter. As the stats member is static, all instances of copy counter will be adding to the same statistics. We also offer an easy way to reset our statistics, and for convenience, this copystats type also has a comparison operator, so you can do 2 measurements and then compare the collected statistics. And finally, I overloaded the streaming operator, so you can easily output your statistics for debugging purposes. To demonstrate, I'll make an instance of copy counter. Let's reset its stats, as otherwise it will already start with a default construction count of 1. And if I now output its stats, you see that everything is 0. If I now create a second copy counter and assign C to it, you see that it recorded the fact that there has been a copy construction. If I would have first created my C2 before doing the assignment, then we have both a default construction and a copy. And of course, if I also do a move, that again is recorded. It's a pretty simple system, but it makes it very easy to keep an eye on how many times something is copied or moved. So, if we now use an instance of copy counter as one of the elements of our tuple, we can track how often this element is copied or moved as we manipulate our tuple. This will help us a lot as we create more and more complex algorithms that manipulate our tuples. Let's see this in action and analyze the copies made during the construction of our current tuple class. If we call makeTuple with the instance of copy counter as our second argument, we see that our copy counter was copied 4 times. That is quite a lot. So let's think for a second, how many copies would we expect? Our copy counter C is passed as an L value, so clearly we are not allowed to move from it. meaning that there must be at least one copy, just to store it in our tuple. But beyond that, there's no reason for additional copies. So let's see if we can find out where these unnecessary copies happen and get rid of them. We start with Metaprogramming itself. We should of course accept our input as a forwarding reference and then forward our input to the tuple constructor. That should reduce the number of copies to 3. And indeed, one fewer, making progress. The deduction guide that is used for finding the correct constructor to call when a tuple is constructed is doing just that. It is not going to be evaluated, so you don't need to worry about it. The actual constructor itself does need some work. We could try to add some ampersands here, but this is not a forwarding reference. Since the type of lm0 is already deduced at this stage, the double ampersand would make this an rvalue reference instead. For a double ampersand to indicate a forwarding reference, there has to be type deduction involved. What we can do is make our constructor a template. Now we can accept our inputs as forwarding references and forward them. And this is where I'm making a mistake. If we freeze the footage for a second, you see that I'm forgetting to add the ampersands, which means that we are accepting our inputs by value, and these forwards will act as std moves. And this is exactly why we've set up this copy counter. It is very easy to miss something and make a mistake when trying to eliminate all the unnecessary copies and moves. And indeed, when I compile, I see one copy, which is expected, but I also see 2 moves that clearly should not happen. If you are a bit less experienced with reasoning about L values and R values, and about when things should be copied or moved, you might not immediately realize that these counts indicate a problem. But luckily, we find ourselves in the very luxurious position where we are implementing something that already has an implementation in the standard library. So, when in doubt, you can just use the copy counter to count the copies when manipulating a standard tuple and compare the recorded statistics. Let's quickly do that. We save our stats, reset the copy counter, and now call std make tuple with our C. If we now output both stats, we see that indeed there are no moves happening in the standard library version of make tuple. So, after scrolling through the code for a bit, I found where I forgot the ampersands and added them. And if we now compile, you see that the stats are exactly the same. Of course, our current tests are not yet perfect. If we really wanted to make sure that our tuple construction and get function work optimally, we should also test them with rvalue inputs, with const references, etc. To make it easier to do so without duplicating a lot of code, we'll create some additional test utilities next episode. And we'll use them when creating our first algorithm to manipulate tuples. I hope you enjoyed this episode and that you'll join me again in the next one. Don't forget to like the video and subscribe if you haven't already. Thanks for watching.